Quantum error correction is one of the most important and challenging concepts in quantum computing. Without it, large-scale and reliable quantum computers would be impossible. In this video, we will explain quantum error correction in clear and simple terms, focusing on why it is needed, how it works in principle, and why it is fundamentally different from error correction in classical computers. To understand quantum error correction, it helps to first understand the problem it is designed to solve. Qubits are extremely fragile. They are highly sensitive to their environment, including heat, electromagnetic radiation, and even tiny vibrations. These interactions cause errors by disturbing the quantum state, leading to loss of information through a process called decoherence. In classical computing, error correction is relatively straightforward. A classical bit is either 0 or 1, and it can be copied freely. If a bit is flipped by noise, redundancy can be used. For example, the same bit can be stored multiple times, and a majority vote can recover the correct value. This approach relies on the ability to read and copy bits without changing them. Quantum systems behave very differently. Qubits cannot be copied due to a fundamental rule called the no-cloning theorem. Measuring a qubit directly also destroys its quantum state. These constraints make classical error correction techniques unusable in the quantum world. Yet errors must still be detected and corrected if quantum computation is to work. Quantum error correction solves this problem in an indirect way. Instead of copying a qubit, the information in a single logical qubit is spread across multiple physical qubits using entanglement. The logical qubit is encoded in the collective state of many qubits rather than any one qubit alone. Errors in quantum systems come in different forms. A qubit can experience a bit flip error, where 0 and 1 are exchanged. It can also experience a phase error, where the relative phase between states changes. Quantum error correction codes are designed to detect and correct both types of errors without directly measuring the quantum information itself. This is achieved through the use of auxiliary qubits, often called ancilla qubits. These qubits are entangled with the data qubits in a carefully designed way. Measurements are performed on the ancilla qubits to extract information about errors, known as error syndromes. Crucially, these measurements reveal whether an error has occurred, but not the actual quantum state being protected. Once an error syndrome is identified, a correction operation can be applied to restore the logical qubit to its intended state. This process can be repeated continuously during a computation, allowing quantum information to be preserved for much longer than would otherwise be possible. One of the simplest examples of quantum error correction is the 3-qubit code. In this scheme, a single logical qubit is encoded across 3 physical qubits. This allows certain types of errors to be detected and corrected. More advanced codes, such as surface codes, use large two-dimensional arrays of qubits and are considered among the most promising approaches for scalable quantum computing. Quantum error correction does not eliminate errors entirely. Instead, it reduces the effective error rate to a level low enough that long computations become feasible. As long as physical error rates are below a certain threshold, error correction can suppress errors faster than they accumulate. Implementing quantum error correction is extremely demanding. It requires precise control, fast measurements, and large numbers of qubits. A single logical qubit may require dozens or even hundreds of physical qubits to protect it effectively. This overhead is one of the main reasons why practical, fault-tolerant quantum computers are still under development. Despite these challenges, significant progress has been made. Experimental systems have demonstrated basic error correction cycles, extended qubit lifetimes, and early versions of fault-tolerant operations. These results confirm that quantum error correction is not just a theoretical idea, but a practical path forward. In simple terms, quantum error correction works by hiding fragile quantum information inside carefully structured entanglement. Errors are detected indirectly, without disturbing the computation, and corrected before they spread. This allows quantum computers to function reliably in an imperfect world. Quantum error correction is essential for unlocking the full potential of quantum computing. Without it, quantum machines would remain limited to small, short-lived experiments. With it, they can scale towards solving real-world problems that are beyond the reach of classical computers. Understanding quantum error correction also highlights a deeper lesson about quantum physics. Information is not just stored in individual particles, but in relationships between them. By protecting these relationships, quantum error correction turns fragility into resilience. As research continues, quantum error correction will remain a central focus. It is the bridge between today's experimental devices and tomorrow's powerful quantum computers. Without this bridge, the promise of quantum computing could never be fully realized.